So joint talk by Alexis Joly, who is from INRIA, and Pierre Bonnet, who is from, I don't have my... CIRAD, sorry. The floor is yours.
Okay. Thank you very much. So thank you, Emmanuel and Gabriel, for the invitation, the organization of the event. So we will introduce progress regarding activity in the development of this PlantNet citizen science platform. So I will introduce the talk, and my colleagues, Alexis, will continue and conclude. So this is a joint initiative among several French research institutes that support through a national consortium, which is now open since a few years, the development of this initiative. So in this first part, we would like to introduce the initial objective on which we have been working. And so the main purpose was to try to compensate the decrease of the number of taxonomists and botanists at the world scale, and to support a new generation of botanists in order to learn more about botany and contribute to produce new botanical observation at a large scale. So we initially experiment the use of multimedia search retrieval engine and image analysis system in order to experiment the development of tools based on that technology that could be shared with the participants in this citizen science project. And so year after year, contribution after contribution, we enlarge a network of participants to this joint initiative that could increase the volume of data, their quality, and then enrich the system and the platform in order to be able to better recognize a new species. So we initiate the project on few dozens of species, and now it covers several dozens of thousands of species at the world level. So the platform is quite largely used. We count around 25 million end users per year. So it is used worldwide with a strong geographical bias, but it's daily used at the world scale, and we manage up to 2 million identification of plant requests per day through this platform. So we estimate that 12% of people use it for professional activities that are illustrated for the largest one that are illustrated here. So this means that more than 80% of users use it for their personal and individual activities, in a sense that they can use it for trekking, during their holiday, during their gardening activity. So it allows this platform to record observation in contexts that are not necessarily covered by expert and professional survey. So the design of the platform was soon motivated by the interest to share the data that we collect, but also the capacity that it offers. So this is why several years ago we started to implement a website that allows partners and developers of application to take benefit of the species identification services that we design, and which is regularly updated based on new validation and new methodologies that we implement. And through a secure API, developers and partners can embed the species identification services in their own workflow application, mobile or web application. So it allows citizen science platform, national biodiversity portal, company who design new products on the mobile market to embed it and to share it with their community of end users. So by this way, for example, people can take benefit of these services and share it with a Spipolien in order to use plant species identification services in a platform that is mainly focused on insect identification. So we have here some illustration of partners who take benefit of these services. So we count around 9,000 accounts who access to these services and who can potentially deploy in a dedicated workflow or application. There is For example, this mobile app Beekeeper, or the other one is Surveyor, developed by CEH, that allows to monitor pollinator communities through the survey of plant species that support this insect and pollinator community. Another example of uses of these services is provided through the reference of the article of colleagues who experiment its potential through, so they analyze the iNaturalist data stream, focus on a specific insect species, and they use the plant species identification services in order to estimate the plant community that were visited by this insect through the visual database that is produced through another platform. So it illustrates how it can be used and transfer and adapt to other purposes than the one for which we develop it. So the main mechanism that we implement is we define it as a collaborative artificial intelligence, in the sense that the end users are part of the development of the model that we regularly train, because they submit images that they can potentially share and validated, and the data are collaboratively validated among the network of users. So this means that we do not use all data share to train the deep learning model, which allows the plant species identification. We mainly rely on the community of end users to revise the quality of the images and the quality of the identification in order to allow to extract the most useful one for the training of the deep learning model that is used, and then the data are shared out of the platform. So when we train the model, it is quite consuming in terms of time and energy. So here on a supercomputer available at a national scale, it takes more than 5 or 6 days to train a model, which is dedicated up to now to recognize more than 50,000 plant species at the world level. So I do not enter in the detail, but there is a regular big change on our side about the architecture that we use to train the model, and we try to follow the most of the state-of-the-art deep learning model to share it with the community of end users, giving them a better user experience and potentially increasing their motivation to contribute to the platform. Plant species identification is a difficult problem due to the fact that there is an irreducible uncertainty in the fact that when you try to recognize the plant species through an images, there is often or several times do not information present on the image that allows a precise identification. So even an expert of each of these groups could not always recognize a species that is usually known on the picture, because on the picture you do not have necessarily all the information to validate the species identification. We have to take into account in the prediction and the use of the prediction of this model for the images that we manage, the fact that we have a strong bias, and one of them is illustrated here. So the most common species for which we have the most higher volume of training data are most well recognized here on the graph on the right, and in green are much better recognized than the one illustrated on the red part of this graph that are illustrated by much less visual data. In order to try to reduce this uncertainty, we implemented last year a strategy that allows to us to post-filter the species identification share to the users through a regional flora and checklist that I provide by Kew Garden through their world checklist of vascular plant. And this has allowed to deploy a system that can be run at the world level, taking into account the most updated plant checklist for each of these regional flora. We embedded also not only a species identification system that just provide a species name, but we enrich it through the use of a visual search engine that illustrated for each species in the results that is provided to the end users the most similar one to the images and identification request that is submitted. So this means that when you submit images of a flower at a particular distance, the level of development, and through a particular angle, you should get in the species identification result the most similar images that we have for each species in the results to the images submitted by the end user. So this increase his capacity to make the correct comparison and to comfort him in the phase of the validation. So end users are also involved in the revision of the quality of the data, so they can vote on so they can share their observation and they can vote on the visual quality of the images shared by the network of participants and also on the species identification shared by the other participant. So we implement a cooperative learning algorithm that allows to take the most probable name for each observation that is shared through the platform. And for that, we define weighted majority voting rules that take into account all the votes shared for a specific observation by the end users community, but we weight each vote according to score which is defined at the end users level. So for each end users, for each profile, we estimate, we have an automated estimation of their expertise, which is defined in here. So for the early career and new end users, their profile have a quite low score, and through their contribution to the platform and the collaborative validation of the observation that they contribute, they increase their the species that they are able to for which they are able to contribute with validated observation. And it illustrated that according to this progress, we take into account more contributions and experts than the others. So through the 1 billion of identification requests that we received since more than 10 years, only half are geolocalized, and through the different filter mechanism, we only use it few million. So here it's illustrated on 1 million through the training of the deep learning model that is used to make plant species prediction. So we have a huge cascade of filter mechanism that allow us to take into account the most fruitful one for the training of the model. All the validated data are shared through a web and mobile portal to provide a picture gallery, distribution of the occurrence. We also start to design and share some graphics that allows to see the temporal, altitudinal frequencies of the observation at each species level. We are well aware about the bias and the geographical, taxonomical bias related to that data, but it allows us to experiment their potential and to identify in which scope then can be the most fruitful one. More than 13 million occurrences are shared through the GBIF in order to allow other community, other scientists from the scientific community to take benefit of this, and this provides us a lot of feedback on their potential reuse out of the platform. So I will now let Alexis continue. Thank you, Alexis.
So thank you, Pierre. So I'm more, my background is more in computer science. So Pierre is the botanist. I'm the informatician. So Pierre talked about what we have now, and I'm going to talk rather about what we are working on currently. And so the first piece of work is about plant communities monitoring. And so we are trying to develop technology that can analyze directly images of multiple specimens, be there quadrant images or roadside images or drone images. So this is quite different from what we are doing in PlantNet, where people take a picture, a close-up of a plant or even of an organ. And here we are more targeting high-resolution images. So that means if you zoom in this image, you have a lot of detail about the plants, but still it's different from the data we have. So first, it's multi-labeled. So it's a multi-label classification task in machine learning, whereas it's a single label classification task. And also there are some shifts of domains in terms of visual content, because the view is not the same, etc., etc. So we have started to try some first experiments where we try to still benefit from the PlantNet model. So the first trial was really to just use the model as it is, but change the input size. So there are some ways in those deep learning models to adapt the input size of the image. And the second technique was whether to do some tiling approach. So you will use the PlantNet model on all the small tiles that we see here in the image. And then we have some technical stuff to aggregate all that in order to make some multi-label classification in the end. And so you can do that without any fine-tuning on those kind of pictures, or you can also try to do it by also fine-tuning the model if you have some multi-labeled data. So typically, if you have images of quadrats with the species, then you can also train the model on this specific data in addition to the classical PlantNet images. But of course, we have very few of them, only for very few species, and so this is less generic. And so here it's an example of an evaluation we made on this side view. So it's vehicle-mounted, car-mounted cameras, vehicle-mounted cameras, that are used in Denmark in the context of a Biodiversity project where they want to monitor invasive species. And so they just produce raw images and they send those images to our technology. And so some of them were labeled manually, allowing to evaluate the performance of the models. So zero shot means that we just use the PlantNet data as training sets, and with fine-tuning means that we also use some of their images to fine-tune the model and get better performance in this particular context. So as you see, the tiling approach is quite good in both cases. And so we are progressing on that. So for this particular context of invasive species, it was rather good, which is probably not the case on many other species like weeds in those kind of images. So we have some ongoing evaluation on such images. But also we try to collect data because we need more data to train effective models for that. And sorry, it's my next slide for the collection of the data. And so we have a citizen science project in France where we try to collect such information. We also try to interact with other existing monitoring schemes, so like Vigiflor, since people do the surveys, just taking a picture is not a big additional effort. So this is like a message today for all of you. If you can have your contributors also take pictures, it could be a way to collaborate. So this tiling approach I show is already integrated in an API, so it's not publicly available, but it's for specific accounts, and we can open it if people are interested. It's already used by the Biodiversity project. We use it also for our participation to the X-Prize Rainforest Challenge. So here it's more for drone images. And also we have developed a web graphical user interface that allows you to manage plots, surveys, so you can upload the pictures, you can have the identification of PlantNet, you can correct manually, you can edit the coverage, you can add geolocation, etc., etc. So we have an operational infrastructure to collect this kind of data. This is done. And so my last part is at an even higher level, which is a tool we are working on called GeoPlantNet, and which is more at the ecotop or habitat level, let's say. And the objective is to produce high-resolution maps of species or of potential distribution of species and related biodiversity indicators. And of course, this is a hard problem because we have a lot of data, but as you know, it's biased in many ways. And also, it's somehow sparse if you look at a particular species, and in particular, the rarest one. And so one way to cope with that, as you know, is to use some species distribution models, where you try to learn the niche of the species, and then to repredict in space where the species could be. But in our case, we are doing something that is in between image recognition and species distribution models, in the sense that the input data we take are not only bioclimatic or environmental data, but it's also remote sensing images, so satellite images, aerial views, altitude images. And so even for the bioclimatic data, we try to use really the spatial information, the landscape information. And we use also here some deep learning technologies. Yeah, I will try to be as fast as possible. And and this allows to train big models that predict the observation or the presence-absence, I will talk a little bit about that, of many species altogether. And so we also organize a challenge about that on Kaggle. This is a platform for machine learning enthusiasts who wants to experiment new models. And so we have shared a big data set, so that includes presence-only data, so our data, but also other data from GBIF, as well as presence-absence data from the European Vegetation Archive. And the test set is real exhaustive surveys from the European Vegetation Archive. So we try to measure in what way those presence-only data can also help to get better predictions in terms of presence-absence at those scales. And as input predictors, we have like a wide variety of either images, but also time series. So deep learning models can capture complex information from such signals. And so we are evaluating all that. And just to try to finish quickly, and we are working in a European project which is called Garden, where we integrate such model to build maps at the European scale and at 50-meter resolution. So there is a lot of engineering work behind that. And this allows to build species maps, so for 10,000 species. Here it's an example of Fraxinus ornus in Greece. Here it's Thymus vulgaris on a finer scale, so you can zoom in the interactive tool around Montpellier. And so if you go even closer, you can see like this distribution of Anthemis maritima on the coast near Montpellier. So the idea is really to have high-resolution maps for local decision makings, like where we could take some concrete action. And from those species assemblage, so at each location you have the set of species, or at least the estimated set of species. And so you can infer some indicators like the tree species richness here, specialization, so number of specialist species in a place, the worst IUCN label of the species of the assemblage, whether there is a species in the EU directive. And then you can select an area and also have the list of species with the number of pixel of cells. It's 50.50 meter cells in which it appears. And we have the same thing for the habitats. So we infer the habitats from the species list based on a species to habitat model. And maybe one future work could be to try inferring which pollinators could be there based on the plants that are there. So we are like looking for good interactions database for that. We are aware of GLOBI, of people, but any good data set for that would be welcome. And maybe I don't have time for that. We are inferring the syndrome of hummingbird from images. So that's an ongoing work jointly with Catherine Graham from WSL. So this worked pretty well. So it's a classification that says if the flower has the syndrome or not, and so you can extend to other species. So, and I'm done. Sorry for the time.